I believe there's a quiz on Friday. Yes, finally. Mm-hmm. Let me silence this alarm. Right now, as you can tell, my voice is a little bit off. I'm in my Lou Rawls phase and heading towards Barry White. Maybe Don Cornelius.
Time for karaoke.
Maybe not. All right, any questions?
We want to ask golf though.
Cough drop. I've had some cough drops. I'm seeing if I can do this without having a cough drop in my mouth the entire class. We'll find out. Thank you, Devin.
So can we ask questions about homework or?
Yes.
So I had a couple where I just didn't really understand the setup of it. Number 26.
Two positive charges, 3 meters apart, total charge. All right, so so you're given two charges, we'll call it Q1 and Q2. And you're told, lost it again, there we go. Total charge is 20 microcoulombs. And they're 3 meters apart. So they also tell you the magnitude of the force. Wrong letter. F sub E. K Q1 Q2 over R squared, which is 9 times 10 to the 9th. Q1 Q2 over 3 squared. And in part A, that's equal to 0.075 newtons. So this is what you're working with. You have two equations, two unknowns. The essence of it, sorry, I just started launching into it based upon past semesters. Did you have a specific question or just general?
No, just keep rolling. Good.
Okay.
I just needed the setup and like how to approach it.
So from this one right here, you saw for Q1 or Q2, it doesn't matter. Q1 is 20 microcoulombs minus Q2. Plug that into here, into there. So you can tell I'm not working at 100% right now. And then you'll have one equation, one unknown. It'll be a quadratic. So I guess we have 20 times 10 to the negative 6 minus, I'm just going to put down Q just because I don't feel like writing. So like Q equal Q2 times Q is equal to 0.075 times 9 divided by 9 billion. Now you get finer tuned if you use 8.99 or there are some exact fractions that you can use. But this is the essence of the problem. Distribute the Q. Bring this whole mess over to the other side. So you end up with negative Q squared plus 20e6 Q minus this equals 0. And then quadratic formula. Now you should get two solutions. But the two solutions should be sort of the opposites of each other because Q1 and Q, you're solving for Q2 here, but we could just as easily solve for Q1. So there should be a symmetry there. So one of the solutions should be Q1 and Q2 equal to some number, and the other solution should be their flipped. And at this point, it's a math problem.
Right.
Is it a Q or a 9 beside the 0?
That right there,
Yeah.
that is a 9, because of the 3 squared. And then part B is a force of attraction, and so the difference is that this would be a negative for part B. And also a different number, but just recognize in part B that since there's a force of attraction, the signs, the Q's have to be opposite signs, and so this one would be negative for part B.
You sick? Or are you tired?
Both.
Coronavirus?
Probably.
Probably. Nice. Did you enjoy some bat soup?
So I just came back from China, and I don't know what the deal is.
Did you have some bat soup over the weekend? Was that some bat soup?
Sorry, I missed it.
Bat soup?
Bat soup? I have not tried that yet.
Oh, you should.
Okay.
It's pretty good.
Thanks for the input. I assume there's some place, Harris Teeter carries that?
I think so, yeah.
All right. I'll go in and ask.
I mean, but for me, I like to go local. I just go in the woods
The woods, okay.
this summer.
Make sure you cook it long enough to get rid of the rabies.
Yeah.
All right.
Have you not seen the picture of bat soup in China? It's like fur and everything.
Sounds yummy.
Bat soup.
That is not funny.
I'm not quite sure what I do. I'd rather eat tripe or bat soup.
It is a delicacy.
Tripe is fish intestines. I guess we can throw haggis in there too. All right. Other questions?
Yeah, it was just a quick one.
Yes.
What was it? I think for 32, just at the end when it says that it's east, is it east because the number is positive, or is it?
For 32,
Yeah.
find the direction and magnitude of the electric field that exerts westward force on an electron. Force does this field exert on the proton? So, your question again?
So it makes sense to me, but just at the end when it says it's going east, like the direction of the final. So I
Right.
just wanted to know if you know it's east because the number's positive.
It depends upon how you set up your convention. So, let's see. They give you the magnitude of the electric field. Oh, they tell you the direction of the force on an electron. So the electric field has to be going in the opposite direction.
Okay, because it's forced on.
And then the direction of the force on the proton would be in the same direction as the electric field, which would have to be east since that was already established.
You're gonna find a roommate.
It's one of those things when you're figuring out the direction for most of this course, there is a matter of the strict adherence to math or just think through it.
Okay.
Other questions? I think I answered your question, Katie, right? Yeah. Okay. No other questions? All right. All right, so I'm gonna sort of summarize at least partly of what we've figured out so far. We've been looking at why objects move, or what is the reaction to, or actually, how do we describe motion between objects? That's poorly worded, but I'm going with it anyway. So if we have two charges, and we're dealing with vectors, we have force. Force requires both charges. And we have formalized E12 is equal to this electrostatic constant, or Coulomb's constant, times Q1, Q2 over R squared, R2 hat. So that's the force on 1 from 2. The units the SI units would be newtons, just like the SI unit for force was in the first semester course. That has not changed. If we're dealing with only one charge, the physicists at the time made up this idea of an electric field, which is equal to that Coulomb's constant, Q1, or just Q, over R squared, R hat. This is the electric field created by Q. The SI unit for electric field is a Newton per Coulomb. And it is in essence just the force, except we divided out a charge. And, well, that's chapter 18 boiled down. Do recognize there's only one physics equation here, that's the force equation. Electric field is based upon that, and so what we have is, like in the first semester course, there was F equals ma, the generalized gravitational formula, and Hooke's law. There were 3 physics equations in the first semester course. Everything else was definitions and math. Same here. I think this course we have 2 equations. This is one of them. 2 physics equations, I should say. Now, if you're dealing with scalars, we have energy, potential energy. Since the electric force is a conservative force, there's a potential energy formula. And use of E. So the electric potential energy is equal to K, so same constant Q1, Q2 over R. Potentially, obviously, we have an empty square here. We should fill it. All right, so questions to here. This is what we did at the end of class on Friday. Questions to here before we add new material.
Is the standard unit still newtons for potential energy?
Oh. What is the SI unit for potential energy?
Yeah.
Yeah, you said Newton?
Yeah.
No, it is not Newton. Flashback. Units of energy.
Joules.
Yes, joules. If you wanted to do it in terms of newtons, it'd be a Newton meter.
I question one after life sometimes.
Okay?
That is really. That was good.
But do you know what would stop her from questioning why she's alive? Taking physics.
That's a good start to this Monday. That was a really good start. Did you get that?
What'd she say?
She was like, sometimes I question why I'm alive.
Sometimes.
Sometimes, oh yeah, sometimes.
All right, so this last bit. Well, think about how we got from force to electric field. We just assumed that there's this property that exists because of a charge, and we just got rid of one of the charges. Well, we're going to do the same thing over here. So we get this Kc Q over R. I'm going to hold off on the single letter abbreviation of that. This is electric potential. Unlike up here, which is electric potential energy. Now, in the first semester course, we could get away with, hey, what's the potential of it? And you knew I meant potential energy. Now, I cannot do that. If I say, what is the potential? I am asking about this down here. I'm not asking about this up here. So, the symbol for this is a capital V. So capital V means electric potential. The units. It doesn't have to be the one word unit, but based upon how we got this, what would the units be in terms of stuff we've done already?
Joules per coulomb.
Yes, so joule per coulomb. Now there is a one word, because that's obviously too much to write. There is a one word, and that is the volt. I do want to point out, we have not talked about voltage yet. Voltage, I have not defined. All right, so let's say this is at 4 volts, this is at 3 volts, this is at 2 volts. I'm going from here to here. What is my change in electric potential?
1 volt. No, negative 1.
I go from 4 to 3,
Negative 1
negative 1. Do the whole thing.
volts.
There we go. So I also want to point out, this is one of those lovely things about physics and math. And I think I mentioned this in the first semester course, but pretending that you have not remembered every single thing that I ever said. If I write V is equal to 4V, in physics class, this means that the electric potential is equal to 4 volts. In math class, V would be equal to 0. These two V's do not mean the same thing, even though it's the same symbol. So how do you know which one we're talking about? Context. Usually the unit comes after a number. That's pretty much the big one. If I go from 4 to 2, what's my change in potential? Yep, so it goes with this one and here. All right, so now let's go on the roundabout trip. I'm starting here, and this particle is moving, and it's going from here, it's going around, moving, goes to the 3, goes to the 3 again, goes to the 4 again, comes around, goes to the 3 again, and ends up here. So with the red path, what is my change in electric potential?
Negative 2.
So it doesn't matter about the path. All I care about is where it started, where it ended. Now, this change in electric potential, some vocab here. Change in electric potential. Also called the electric potential difference. And I'm going to put electric in parentheses because given the context, oftentimes I'll just drop the word electric because that's the topic we're talking about right now. So if I say potential difference, hopefully you're thinking, oh, this is physics 152. Of course, he's talking about electric potential difference. But this also has another name. That is voltage. Now, oftentimes, textbooks will use voltage and potential interchangeably. And again, what's the justification? Well, if my voltage is equal to change in potential, which is VF minus VI, what we establish as 0 is anything we feel like. So just like with potential energy, we can establish 0 where we want. So if VI equals 0 volts, then delta V is equal to the final V, or since now we're only dealing with 1. And so oftentimes these are just used interchangeably. It's fun when a textbook will suddenly just make a delta go away. Some textbooks are very retentive about that, and they make sure the delta's in there everywhere it should be. Some textbooks are fast and loose. I think your textbook is fast and loose. So just please be aware about when it really should be a V and when it should be delta V. Questions at the moment? I have a charge here of, let's make it 112, no. 2 nanocoulombs. If I am 1 meter away, what's the potential here? What is the electric potential at that spot, 1 meter away? And although there's at least 2 people with a calculator out, it can be done in your head. But
Oh,
no, if you have to use a calculator at this point, that's fine. Just recognize why I picked nano.
I didn't see that. Oh.
And anyone?
18 volts.
Yep, 18 volts. It's just straight plug into the formula right here. Coulomb's constant is 9 times 10 to the 9th times 2 times 10 to the negative 9th divided by 1. Those cancel out, and I'm left with 18. Suppose we go an additional 1 meter away.
9 volts. Or, yeah.
We go an additional 1 meter away.
6 volts, 6, yeah.
An additional 1 meter away.
Whatever 18 divided by 4 is.
Oh. I'm not addicted to a calculator, I can stop anytime.
4.5 volts.
Thank you. It's okay, Joe. There are groups out there that can help you.
I feel like my Asian hands.
All right. If I put a proton here, based on the other stuff that we've done, which way is it going to go? I got 2 fingers pointing to in a particular same direction, which is nice. 3, 4. I'm assuming. Okay. We got a groundswell of 4, and everyone's just sort of staring. If I have a positive charge here, and I put a proton here. Which way will the proton go? Okay, got a couple more fingers on that one. And again, some people just staring. I don't know whether it's because you just don't feel like participating, or whether you're not quite sure what happens when 2 positive charges are near each other. Darn, let me pick on you, Brenda. Put a positive charge here and have a positive charge here. Which way will the proton go? Yeah, I was just wondering why you were quiet before. I'm sorry, you have to talk louder
I
today.
don't feel like lifting.
Okay, got it. I'm sorry to have made you do that then. All right, it'll go this way. But we can generalize it though, is that positive charges in the presence of electric potential will move to the lower potential. So positive charges move to want to move to lower potential. And negative charge is the opposite. That's half of it.
And that's only if the charge is positive.
If
Like
that,
that charge is positive.
then it'll move away. It's still gonna move to a lower potential regardless.
Okay.
Because if this is a negative charge, so let's make this a negative 2, then what does this become?
Negative
Negative
18,
18.
negative 9, negative 6, negative 4.5.
All right. In which case, if I put a proton here, which way is the proton gonna go now?
Left.
And it's still moving to a lower potential.
Okay.
So we now have, well, an essence of batteries right there. Questions on this before I erase? So the other part of it, as sort of laid out right there, is that positive charges want to move to lower potential. Negative charges want to move to higher potential. The opposite, surprise, surprise. Moving away from positive, I'm just gonna put a big Q there, from positive to differentiate them. Yields lower potential. And then moving away from negative Q yields higher potential. Or toward negative Q yields lower potential, whichever way you want to do it.
Since you said that they want to move, does that mean there are instances where they don't?
A case would be if I've got a negative charge here and I take an electron, for example. If I said, what if I put an electron here, which way would the electron go? Right. However, I could shoot the electron at it, in which case it will get closer, but it's going to start slowing down. If I shoot a proton at it, that proton's going to get faster and faster.
You said moving towards negative Q yields higher potential, right? Or is it?
Now, moving towards a negative Q, the source, is going to yield a lower,
Oh, so moving away from negative Q would.
yields higher.
Yeah. Okay. Cool.
Thus, an electron, if I put an electron near a negative charge, it wants to move to a higher potential, and so it'll move away. And oftentimes, if you just think through the forces, the opposites attract, like repels, and then sort of work backwards into remembering these rules. There was one test I did a couple years ago where I asked what's the voltage between 2 points, and then I asked what's the electric potential difference between the same 2 points, and it should have been the same answer. Not everyone saw it that way. So if I take a battery, there's a positive and negative end. And let's make this a 12 volt, just don't have to do decimals. I got a 12 volt battery here with a positive and negative end. They labeled it in a way that makes sense to me. The positive side is the higher potential, the negative side is the lower potential. Higher V, lower V. That 12 volts there is not the potential of the battery. It is the potential difference. This is the voltage. It is the difference between these two. So I have no idea what the actual potential at the bottom is. All I know is that the top here is 12 more. So if that's 100, this would be,
112.
if this is 0 at the top, what is this?
Negative 12.
So there is a certain arbitrariness to where you'd establish 0 is. Now there is a convention that we will eventually get to. It's called, if you've given a circuit and something is grounded, that generally is where you're establishing a 0. But again, there's a certain arbitrary, that's convention more than physics law. All right, so what do you suppose makes the negative end of a battery negative?
Surplus of electrons?
Absolutely. You got a whole bunch of electrons right here. And what makes the positive side positive?
Protons.
A lack of electrons.
I heard protons and I was going with that. There were several other things that I missed, so I apologize. Here's not as stopped up as usual at this point, but it could just be my hearing. So if I got all these positive charges here, negative charges here, why don't these negative charges go zipping up into the positive charge?
Because there's stuff in the battery.
Yes, fortunately, there is stuff in the battery. So there is a barrier here to prevent it. Now for the rechargeable batteries, you can force things to go through it, and thus you can sort of separate them to recharge a battery. Over time, that barrier starts to degrade for the rechargeable batteries. And then you've got just the plain old disposable batteries, where the battery doesn't degrade, but at some point, all these electrons, at some point, this gets neutralized. So if I take a wire here and connect it from here to here, what is going to happen?
The electrons are going to go through the wire to get to the positive side.
All right. So first thing is going to happen, yes, the electron here is going to go into that, leaving a hole. And then the electron here is going to fill that, leaving a hole. And then electron here is going to fill that up, leaving another hole. And basically you have electrons traveling this way, and then you have a hole traveling that way. Now, the physical thing that's moving based on our current theories is that it is the electron that moves. However, you will occasionally see people write H plus to indicate it is a hole that is moving in the opposite direction. And now, sorry?
How does a hole move? Like, what do you mean by that?
All right, so if I've got a bunch of spaces here, and I have electron here, and I got some big positive charge over here, they're attracted. This electron can't move into this space because there's an electron there already. Matter of fact, none of these can move. This is the only one that can move, really. So that one will jump into that space, leaving a hole there. So the hole was here, and then the hole is now here. And then that electron will fill that space, and that hole is now here. And so that's what we're talking about. Other questions right now? All right, enter Ben Franklin. Or return back to Ben Franklin. Ben Franklin thought that current flows from a high potential to a low potential, and it makes sense from what he knew at the time. Water flows from a high spot to a low spot. He was thinking of what was moving was some sort of fluid that would flow from a high spot to a low spot. And so he established, so once he established all this stuff, he said, well, current's flowing this way.